Hello everybody, welcome to this channel. I'm Mehdi and I'm excited to explore the fascinating world of chemical bonds with you today. So let's get started. Right, I'm gonna start with the concept of electronegativity. This is a key property that helps us understand how elements interact with each other during chemical bondings. Electronegativity is a measure of an atom's ability to attract electrons in a chemical bond. It ranges from 0.7 to 4 on the Pauling scale. Elements with lower electronegativity values like cesium, which has an electronegativity of about zero point 0.7, have a weaker ability to attract electrons. On the other hand, elements with higher electronegativity values like fluorine, which is the most electronegative element at 4, have a strong ability to attract electrons. So, why does this matter? Smaller electronegativity values indicate that the element is more electropositive. These elements are likely to lose electrons and form positive ions. For example, elements like sodium and potassium fall into this category and readily give up their electrons in reactions. Conversely, larger electronegativity values signify that the element is more electronegative and will likely gain electrons to form negative ions. This is common in elements like oxygen and chlorine, which want to get electrons to fill their outer shell. Now, let's explore the ionization process, which is fundamental to understanding how elements interact to form compounds. In this process, we typically have a metal atom that donates electrons and a non-metal atom that accepts those electrons. This interaction usually occurs between elements with dissimilar electronegativities. When the metal donates electrons, it becomes a positively charged ion or cation. And when the nonmetal accepts electrons, it becomes a negatively charged ion or anion. So let's look at an example using magnesium oxide. Here's how it breaks down. Mg has the electron configuration of 1s2, 2s2, 2p6, 3s2. This can also be represented as Ne3s2. Magnesium has two valence electrons in its outer shell, which is eager to lose. When magnesium donates these two electrons, it forms a Mg2 plus ion with the configuration 1s2, 2s2, 2p6, which is equivalent to the noble gas neon. Now, let's consider oxygen. Its electron configuration is 1s2, 2s2, 2p4. Oxygen needs two more electrons to complete its outer shell, giving it a total of 6 valence electrons. When oxygen accepts those two electrons from magnesium, it becomes an O2 minus ion with the electron configuration 1s2, 2s2, 2p6, also equivalent to Ne. So, after the ionization process, we have Mg converted Mg2 plus loses 2 electrons and O plus 2 electron converts to O2 minus, gains 2 electrons. To sum it up, the ionization process is key in forming ionic compounds like magnesium oxide. The transfer of electrons allows the participating atoms to achieve a stable electron configuration. like noble gases, leading to the formation of ionic bonds. Now let's talk about ionic bonding, which is a crucial concept in material science and chemistry. Ionic bonding happens between positively charged ions, I mean cations, and negatively charged ones, or anions. This bond is formed through the transfer of electrons from one atom to another, which creates these charged particles. One key point to remember is that a large difference in electronegativity between the two atoms involved is required for ionic bonding to take place. This significant difference leads to the metal atom losing its electrons and the nonmetal one gaining them. So, let's take a closer look at the common example, sodium chloride, NaCl. You know, sodium being a metal has an unstable electron configuration with one electron in its outer shell. It wants to lose this electron to achieve a more stable configuration. On the other hand, chlorine is a nonmetal that also has an unstable configuration, needing one more electron to complete its outer shell. When sodium donates its electron to chlorine, it transforms into an Na plus ion, a cation, and chlorine becomes a Cl minus ion, an anion. So, at this point, we can say Na is transferred to Na plus, loses one electron, and Cl plus one electron is going to be Cl minus because it gains one electron. So this electron transfer results in both ions achieving stable configurations. Now we have stable Na ion and stable Cl ion. The attraction between these oppositely charged ions is known as Coulombic attraction, which is a powerful force that holds them together, forming a strong ionic bond. Well, let's focus deeper into the concept of ionic bonding by discussing the energy aspects involved in the formation of ionic compounds. When we talk about ionic bonding, we need to consider the energy involved. The most stable ionic structure is achieved at a state of minimum energy. This is when the net energy of the system is at its lowest point, balancing the attractive and repulsive forces between the ions. The net energy of an ionic bond can be understood as the sum of two types of energies. Attractive energy, using E sub A, which rises from the attraction between the positively charged cation and the negatively charged anion. Repulsive energy, shown by E sub r, which comes into play when the electron clouds of two ions begin to overlap, pushing them apart. So, the relationship between these energies can be expressed mathematically as En equals Ea plus Er, which is equal to minus A over R plus B over R to the power of N. So En is the net energy, Ea is the attractive energy, Er is the repulsive energy, R is the interatomic separation. A and B are constants related to the specific ions involved, and N typically has a value of 12 for ionic compounds. At the point of equilibrium separation, the net energy is at a minimum, indicating a stable ionic bond. This means the attractive forces between the ions perfectly balance out the repulsive forces, resulting in a stable ionic lattice structure. Now, Let's talk about covalent bonding and see how it differs from ionic bonding. Covalent bonds form between atoms with similar electronegativities. When atoms have comparable electronegativities, they prefer to share electrons rather than transfer them. This sharing allows both atoms to achieve a more stable electron configuration. Typically, covalent bonds involve valence electrons, specifically those in the s and p orbitals. A great example to illustrate this is H2 molecule. Each hydrogen atom has one valence electron and needs one more to fill its outer shell. Since both hydrogen atoms have the same electronegativity, they come together to share their electrons. Here is how it works. The first hydrogen atom contributes its 1s electron, and the second hydrogen atom contributes its 1s electron as well. By sharing these electrons, they form a stable bond known as a covalent bond. So, in essence, the hydrogen molecule is formed by the overlap of these two 1s orbitals, creating a bond that holds the two hydrogen atoms together. Next, let's discuss an interesting concept in covalent bonding, bond hybridization. This process is particularly important for understanding how certain elements like carbon can form different types of bonds. Hybridization happens when atomic orbitals mix to form new equivalent orbitals called hybrid orbitals. Carbon is a great example because it can form sp3 hybrid orbitals. Here is how it works. Carbon has the electron configuration of 1s2, 2s2, 2p2. To form four equivalent bonds, one of the 2s electrons gets promoted to the empty 2p orbital. This promotion results in four orbitals that are all equivalent in energy, and we call them sp3 hybrid orbitals. The geometry of these sp3 hybrid orbitals is important. They arrange themselves in a tetrahedral shape with bond angles of approximately 109.5 degrees. This geometry allows carbon to bond effectively with four other atoms. Let's continue our discussion of covalent bonding by focusing on hybrid sp3 bonding, specifically involving carbon. As I mentioned earlier, carbon has four valence electrons and needs four more to complete its outer shell. Here is the breakdown. It has four valence electrons in its outer shell, but requires four additional electrons to fill that shell. Hydrogen, on the other hand, has one valence electron and also needs one more to achieve a stable electron configuration. Now, the fascinating part is that the electronegativities of carbon and hydrogen are quite similar. This similarity allows them to share electrons rather than transferring them, resulting in the formation of sp3 hybrid covalent bonds. In the case of CH4, the bonding process looks like this. Each of the four hydrogen atoms shares its single valence electron with the carbon atom. Carbon uses its sp3 hybrid orbitals to form four equivalent bonds, resulting in a stable molecular structure. This arrangement creates a tetrahedral geometry where the bond angles between the hydrogen atoms are 109.5 degrees. Well, let's shift our focus to metallic bonding, which is quite different from the covalent and ionic bonds we have discussed so far. In metallic bonding, we have a unique scenario where electrons are delocalized. creating what we refer to as an electron cloud. This delocalization means that the valence electrons are not tied to any specific atom, but are instead shared among all the atoms in the metal. Here is how it works. The positively charged ion cores of metal atoms are surrounded by these sea valence electrons. These electrons are free to move throughout the metal, contributing to the properties we associate with metals like conductivity and malleability. To visualize this, think of the metal as a collection of positively charged ions sitting in a soup of free moving electrons. This arrangement allows the metal to conduct electricity efficiently because the electrons can move freely in response to an electric field. Next, let's dive into mixed bonding, which is quite interesting because it combines characteristics of both ionic and covalent bonding. The most common type of mixed bonding we face is covalent ionic mixed bonding. Now, you might wonder how we can quantify the degree of ionic character in a bond. We use a formula that involves the electronegativities of two elements involved in the bond. The formula is ionic character percentage is equal to 1 minus e to the power of negative xa minus xp squared divided by 4 times 100%. So Xa and Xp are the electronegativities of the two elements participating in the bond. The result gives us a percentage that indicates how much of the bond is ionic in nature. Let's look at a specific example, magnesium oxide. The electronegativity of magnesium is 1.2 and the electronegativity of oxygen is 3.5. So, using this formula, the bond in MgO has a significant ionic character, about 73.3%. Now, let's explore secondary bonding, which is a fascinating topic because it highlights how attractive forces can arise even in materials that don't have a strong primary bond. So, what is secondary bonding? It arises from the attractive forces between dipoles. Dipoles can be created in a couple of ways. For example, fluctuating dipoles occur when the electron clouds around atoms are asymmetrical. Think about it. At any given moment, the electron in an atom might not be evenly distributed, leading to a temporary dipole. A classic example of this is liquid hydrogen, where these temporary dipoles create weak attraction between molecules. We may have a permanent dipoles. They happen when molecules have a permanent separation of charge resulting in a positive and a negative end. A great example here is liquid, hydrochloric acid. In HCl, we have a hydrogen atom that is less electronegative than chlorine. So we have a dipole, the hydrogen end becomes slightly positive, and the chlorine end becomes slightly negative. This permanent dipole leads to secondary bonding between molecules. Another interesting aspect of secondary bonding is its significance in polymers. For example, consider a linear polymer molecule. These long chains can have secondary bonding interactions between their repeating units, which influence the properties of that polymer. So, why is secondary bonding important? It affects the overall physical properties of materials, including boiling points, melting points, and sometimes mechanical properties. Now, let's focus on the properties related to bonding, focusing on melting temperature and how it relates to bound length and bound energy. So, first off, melting temperature, or Tm, is a key property of materials that tells us how much energy we need to apply to break the bonds holding the material together. The melting point is significantly influenced by the type and strength of the bonds in a material. Now, let's talk about bond length, R. This is the distance between the nuclei of two bonded atoms. Imagine it like a tiny resistor in an electrical circuit, where the length can impact how electricity flows. Similarly, the bond length affects how easily atoms can vibrate and move apart. To illustrate, we can look at a graph that shows energy as a function of bond length. As we bring two atoms closer together, their energy decreases due to attractive forces until we reach a minimum energy point. This point corresponds to the bound energy, or E0. Beyond this optimal distance, we push the atoms closer, we see an increase in energy due to repulsive forces, leading to instability. Well, let's continue exploring the properties related to bonding, this time focusing on the coefficient of thermal expansion, alpha L. This property describes how materials change in size with temperature changes, which is important in many engineering applications. Coefficient of thermal expansion quantifies how much a material expands per unit length for a given temperature change. The relationship can be expressed as delta L over L0 equals alpha L times T2 minus T1. Here, delta L is the change in length, L0 is the original length before heating, T1 is the initial temperature, and T2 is the final temperature after heating. So, as you increase the temperature of a material, its length increases based on this coefficient. So, let's connect this to bond energy. As we discussed before, E0 represents the bond energy. Interestingly, the relationship between bond energy and thermal expansion is inversely proportional. The smaller the bond energy, the larger the coefficient of thermal expansion. It means that materials with weaker bonds will expand more when heated compared to the materials with stronger bonds. Why does this happen? When the bond energy is lower, there is a greater asymmetry in the energy versus bond length curve. This thing allows the atoms to move apart more easily when heat is applied, resulting in a greater increase in length and therefore a larger alpha L. Okay, let's wrap up our discussion by summarizing how different bonding types and bonding energies influences the properties of materials, particularly focusing on ceramics, metals, and polymers. Ceramics, which primarily exhibit ionic and covalent bonding, have strong bonds that contribute to their high melting temperatures and low thermal expansion. This makes them ideal for high temperature applications. Metals have a more flexible bonding structure, leading to changing properties. Their melting temperatures and thermal expansion coefficients fall between those of ceramics and polymers, making them versatile in various applications. And polymers exhibit weak secondary bonding between their chain, which significantly impacts their physical properties. They have low melting temperatures and a high coefficient of thermal expansion, making them suitable for applications where flexibility and lightweight are advantages. Right? If you enjoyed learning about how different bonds influence material properties, please like, share, and subscribe for more engaging content in material science and engineering. Your support helped me continue exploring these important topics together. See ya.